it transport into nucleus like that.
Okay.
But here A and BC are both three are in the cytoplasm itself. So is the image is correct or not?
Sorry, Jaram, I do not have access to this year's assignment, so I have to look into the question and get back to you. Can you just tell me the question number and?
The first question, identify the mistake in the graphical model given below.
Okay, okay. I have to check and get back to you because I do not have access to the assignments right now.
Okay.
So I'll check it and I'll get back to you. Okay.
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 Thank
Either
you.
next week or you remind me once in next week as well. I'll get back to you. Okay.
Sir, I have a request to please kindly take care of these questions also.
The thing
Because
is, I am instructed not to give out answers of assignments because those
okay.
assignments are graded, and later you will be provided with an answer sheet. Obviously, the solutions and everything will be provided by the NPTEL folks only. I am instructed not to discuss current assignments because like those are graded. So I do not have access to this assignment. So I have to take a look and I'll have to come back again. Okay. If you have any
Okay.
problem, you have to like
So
tell me. I'll see
can
and
we ask some questions from you in this section?
questions from. Sorry.
Can we ask these? Can we discuss with you these questions
Yeah,
during your
we
lecture?
can discuss once these 4 weeks are over. So I'll take another 2 hour extra live session where we'll cover up the whole course. In that session, we can discuss all these assignments. But right now, since these are graded, I cannot discuss this and put it on YouTube, right? So uh,
Okay.
I'll discuss these in the later videos. Okay.
Okay, sir.
Okay.
Okay.
Okay. So let's get started for today. Okay. So, hi again. Welcome to the second week of this course. I'm taking the live session. So, my name is Shomo, and today I'll discuss what has been covered in week two. So, mostly the topics include steady states and how we calculate steady states. What is actually the steady state meaning, and how we calculate those using differential equations. How we graphically visualize those using direction fields and phase planes and etc. And I'll also go through a little bit about using JSIM as a software. So I hope all of you have gotten access to the software because it was linked in the course itself. If not, I'll just put the link here. You can sorry. Ah, this is the link. So if you have not installed JSIM yet, please use this link to install, and towards the end of this live session we'll discuss about JSIM and how to like simulate your models there. One thing sir has asked me to inform you that uh, although you will not be asked to asked to use JSIM as a practical exam, nothing of that sort, but what we will be given is JSIM code, and you will be asked maybe some small questions from that. So being familiar with JSIM is also important. Just to give you a heads up, you will not be asked to write big codes or simulate models, but you'll be asked to take ask small questions regarding codes and everything else in JSIM. So please go through JSIM as well. So yeah, other than that, we'll cover steady states and how we uh, can visually represent and solve these problems. So okay, let's get started. So firstly, what is a steady state? So steady state as a definition are those points or equilibrium points, as we say, where the value of your dependent variable, which is I've denoted n here, but most of the times you'll see as x. So where the values of a dependent variable does not change with time. So basically dn dt or dx dt will always be 0. So dn dt or dx dt represents the rate of change of x with respect to time. So if dn dt or dx dt equal to 0, what it signifies is your x or your n, whatever your dependent variable is not changing with time. It is at an equilibrium position, or what we call as steady state. So in simpler terms, steady state is the state where the system isn't changing over time. So it's a state of the system where it is very comfortable to be in and it does not want to change its state. So that's where the steady state is, and it is not changing with time. So one such example of steady state that we see in biological or chemical systems is chemical equilibria. I hope many people are familiar with this concept of chemical equilibrium. So you have two reactions, one a forward reaction, one a backward reaction, but the rate of the reaction of the forward and the backward are equal. So essentially the reaction is at a standstill, which is called as the chemical equilibrium. So similar is a concept that we see here. There also we call it steady state of the equilibrium. So here also what we define is that our system is not changing with time, so that's why it's in a steady state. So now steady states can be either stable or unstable. So there can be majorly two types of steady states. So I agree that the state is there where the system is not changing with time, but another question to add to that is, does the system want to remain in that state, or if you just perturb it or push it a little bit out of that stage, it will not come back to that stage again, or if you just perturb it or push it a little bit out of the stage, will it come back to the state again? So that is a question, another question that that comes up for steady states. So we define two kinds of steady states. One is a stable and the other is unstable. So stable steady states are those where if a small disturbance away from the steady state causes the system to return to the steady state over time, then the steady state is stable. Where I'll come to this example in the next slide, so I'm not reading it out here. And another type of steady state is an unstable steady state, where basically a small disturbance can cause the system to move further away from the steady state and it won't come back to the steady state. So that is what is unstable steady state. So here is a very good example of stable and unstable steady states. So basically there are three states, as you can see. You can imagine this as this S1, U1 and S2 are three balls, and this is a hilly structure, you can imagine. So on top of this hill there is this ball U1, which is not moving because it's in a state of equilibrium. Same is the case with S1 and S2 as well, where the states are in a state of equilibrium, so it is not changing its state over time. So dx dt or dn dt here is 0. But all three are not the same exact steady state. So as you can see, if you imagine, if you are just pushing the ball S1 towards one side, either side, be it left, so be it left or be it right. If you want to push the ball S1 to the left or the right, the ball will straight come back to where it was, which is the bottom of this trench. But the case with U1 is not exactly the same, it's kind of opposite. So if U1 is also an equilibrium state, but if you push U1 a little bit, it will fall off this cliff or it will fall off this cliff, and it won't naturally come back to its position because this is a higher energy position. So this is what is called as unstable steady state or unstable equilibrium. And S1 and S2, which are basically stable equilibrium or stable steady states, because if you perturb this steady state, the system will tend to come back to its original position. So this is a very good example of how we define stable and unstable steady states, what we mean by stable and unstable steady states. Okay, so again, after stability there comes what is called as an attractiveness. I'll not go into the detail, but just to give you an idea about what we mean by that. So if the position of the steady state, so for example this position or this position, if the position of the steady state attracts the component of the state back to itself, say for example in this steady state, if you move it to right, the S1 will come back to its original position. So this position of the state is what is known as an attractive steady state. And for unstable steady states, if you push the ball a little bit, it will flow over and it will not come back naturally to its original position. So it's what is called as a repulsive steady state. So what we discussed is what are steady states, how do we define steady states, and what do we actually mean by steady states, and what are the different types of steady states, stable, unstable, and why are we looking into these. We'll come to it a little bit later, but what happens is steady states are very important important points in the graph. Basically, as you have seen, we visualize steady states in a graph. So those are very important points in the graphs where you are trying to model an equation. What you want to find is where ultimately is your system going to converge over time. So if your time, you have unlimited time on your hand, where is your system going? Is it going to a stable steady state, or if it is an unstable steady state, you can assume that it will not remain there for a long time. It can move away with the slightest perturbation. So these kind of ideas, what kind of situation is the system in, is very important when you're trying to answer certain questions using modeling. So when you're trying to answer, say for example, in a predator-prey system, or in a say for example in a predator-prey system, at time t equal to infinity, what will be the concentration of the predator or the prey in the system? So these kind of questions, what you want to find out is, over prolonged amount of time, where is your system going to converge, or is it either going to converge, even going to converge or not? These are the kind of questions that are answered by solutions of steady states, and that's why we look into steady states. Okay, so moving on, I'll just go over certain things here, but I'll come back to these things when we are doing certain examples. I just want to give you an idea of everything first, then we'll solve some examples so that you can understand it better. Okay, so first here is basically, for example, take this equation dx dt equal to f of x and t. So in most cases, this is how in real life situations you'll find your models looking like. So your left hand side is giving you the rate of change of your dependent variable over time, and the right side is basically an equation describing that change. Now that equation might contain x and t both, or it might contain either x or t. So if it is containing x and t both, it becomes a little bit more difficult to manually integrate or find the solutions of these systems. So what we'll do for our case is, basically we'll assume that the right hand side does not have a t term in it, so just an x term, and this is how we'll proceed for the further examples as well. So this is the autonomous case that we are defining here. So how do you find a steady state of a system of a system given by a equation like this, dx dt equal to fx? So this is quite straightforward. So what your idea in steady state is, dx dt equal to 0, or dy dt, or whatever your independent variable is, the rate of change of that variable with time. I misspoke, it is your dependent variable. So x is your dependent variable here, t is your independent variable, not to be confused with. Okay, so dx dt is what is giving you what is your dependent variable is changing your with time, and it is given by this fx equation. So if you want to find the steady state of this system, it's quite straightforward. You know that at steady state dx dt will be 0, which in turn means fx will be 0. So steady states will be where fx equal to 0. Just to keep in mind, do not confuse, fx is not of it's basically not describing the function, the relationship between x and t. What it is denoting here is a relationship between dx dt and x, just to be clear. So fx, when we do integrations and differentiations, what we start with is a y equal to fx kind of a thing, and then we differentiate y. So dy dx, we differentiate the right hand side as well. So f dash x, what we call is the d dx. So one differentiation you do, d dx of fx. So here, just to keep in mind, your fx is just the function that is describing dx dt. It's not a function that describing x and t. Okay, so it is a relationship between dx dt and x. It's not a relationship between x and t. Okay, and just to be clear here. So this can be t as well. So it can be a relationship between dx dt and x and t, but not just x and t. Okay, so here it is quite straightforward. You just equate this function on your right to 0, and what you get is a phase line diagram. So where x is increasing or decreasing across the steady states. We'll come to this a little bit later. and it relies on being able to sketch the plot of sketch or plot the graph of fx. So if your fx, this is your fx and this is your x. So if basically your dx dt is given as fx, so it's basically your y-axis is dx dt, don't get confused. Your y-axis is dx dt and your x-axis is x. So what this plot is showing you, how your dx dt is changing with x. So as you can see, if function is like this is what we call an oscillatory function, that's because it passes through, say for example, this curve passes through the x-axis. The x-axis is denoted by y equal to 0. So this curve passes through x-axis at different points. So at y equal to 0 is the whole line, so you have 4 points where x have different values. So this is what we call an oscillatory function, or which has a time period with it. So after a certain time it repeats itself. So say for example, this is time t equal to 1, this is time t equal to 2, and again at time t equal to 3 the system comes back to its older position. So this is what it is determining. But to remember, your dx dt and x is what you are plotting here. So at and everywhere your y is 0, your y-axis is 0, is basically your x-axis. So every point at which fx or dx dt is equal to 0, these points are actually denoting your stable states, just to be clear. So this is your curve which is denoting your relationship between dx dt and x, and every point this curve meets x-axis where it is y equal to 0, it is giving you steady states. These are your steady states, because at these points your dx dt equal to 0 is how you define your steady state. So what you want to see along with this, from this curve it is very clear where the steady states are. But after this, what you want to know is how is the area around the steady state. Is your dx dt, your slope, increasing or decreasing around the steady state? So that's how you can predict if the system, if moved from that steady state, will come back to that state or not. So the sign of dx dt in and around these steady states are very important to tell you if the steady state is stable or not. So we'll look through an example later, but yeah, this is the whole idea. Okay, you plot your dx dt versus x and you check at each point where your dx dt is 0. These are your points where dx dt is 0, and then after that what you check is around these points, is your dx dt increasing or decreasing. Depending on that, you can tell the states to be stable steady states or unstable steady states. Okay. So what it tells you is, basically what you want to know is how fast is your x increasing or decreasing. And this, the easiest way to do is with graphical arrows. So the arrows left to right is showing that it is increasing, and for arrows right for x increasing, and this reinforces our understanding in stability or instability. So what happens is, say for example, take this point. So at this point it is the steady state, this is a steady state, but here the slope of the of the area around the steady state, so these area, so here the slope is of one direction and here the slope is of another direction. So basically what is happen is, you have your steady state at one point. Around that point, x at one side, on your left x is increasing, on your right side x is decreasing. So basically what is happening is, you are moving away from that steady state. So you are come to a steady state. What you are doing is, around the steady state you are checking what kind of slope is there. So if it is moving, if both the slopes are moving away from the steady state, what it means is it's actually an unstable steady state. Remember how we define unstable steady state? So unstable steady states are those states where you slightly perturb the system moves further away from the state. So that is how we are going to define unstable and stable steady state. So for example, this is a stable steady state because here the slopes around the steady state is either decreasing towards the steady states actually. So if your states is in any vicinity of your steady state, it will go over time, it will go and converge to that state. That is the whole idea. So the whole idea is basically you have a steady state. What you want to do is you want to check its vicinity. If my system is not in the steady state, it is around the vicinity of the steady state, will it come and converge to the steady state over time or not? If it does, it's stable. If it doesn't, it's unstable. We'll look into it through more mathematical nuances, but I just wanted to give you an idea about how we think about stable and unstable steady states in terms of graphical representations. Okay. So let's okay. Say for example, you have what we next will learn is what are slope and direction fields. So basically how we can find steady states using slopes and direction fields. So first let's consider an equation like this. Say for example dy dx, it's given, it's basically dy dx, it's given as x plus y. So this representation is basically if there is one dash on top of your variable, what it means it's been differentiated once. If there are two dashes, it's differentiated twice, three and more, it's intuitive enough. So this is the equation. What it is showing is dy dx equal to x plus y. Now how from this equation alone we can deduce some facts about the solution of this equation. So geometrically speaking, the value of the first derivative of a function at a point is slope of the tangent line to the curve of the function at that point. We know that. So at any point in the curve, if you differentiate and find the tangent of that curve along that point is what is your slope. So your equation is given something like this. So it's very similar to what we saw just earlier. Here, this basically this is what it is representing here. Y dash equal to f of xy. Now you can interpret the value of f of AB. A and B are 2 points. Is a point in the space of xy. What you can do is you can interpret the value of this FAB as the slope of the tangent line to the graph of your function at the point a comma b. So what this will tell you is basically the slope of any solution passing through a given point. So this is, if this is your differential equation, y dash equal to x plus y, you can pick up points, random points in the plane and compute the slope. So what will be the slope here? It's just y dash, it is given. Your slope is already given by your differential equation. You just need to substitute the values of x and y at, say for example, at 1 1. This here will somewhere will be 1 1, the point 1 1. Now if you want to find the slope of the curve at your point 1 comma 1, what you need to do is just put in x equal to 1 and y equal to 1 in this equation, because your y dash, which is your basically dy dx or your slope of the tangent of a point, is already given by this equation x plus y. So you just plug in 1 plus 1 equal to 2. So your slope at x equal to 1 and y equal to 1 will be 2. Now you can do it with any random points in the whole quadrant. So you can pick up, say for example, -2 comma -2, or in this quadrant as well, say 2 comma -2, something like this. What you can do is across a whole space you can pick up different points and you can check the slope of the curve at that particular point. So, and according to the slope you put these arrows. What these arrows are showing are basically small lines which are representing the slope or the angle at which the tangent is with the curve. So this is how the slopes are looking like here. So these are all positive slopes, as you can see. But these on your like fourth quadrant, so basically this is first, second, third and fourth quadrant, you can see these slopes are all negative here. These slopes are all negative. These are some negative, some are very close to 0, and on your second quadrant you have a mix of both positive and negative slopes. So what you can see is, using this whole plane, is what you have done is you have checked the possible slope of the curve at every point in your plane. So what do you see from here? Say for example your system starts here. There either the system can follow this path and go like this, or the system can follow this path and go like this. So what you can see from this phase planes or direction fields or slope fields, whatever you want to call it, what it tells you is how your system is evolving over time. You do not know the exact position of the system with time, but what you can do is you can have an estimate. Okay, if I keep this system in the same sort of conditions for a longer period of time, what will happen to my system? Where will my system go and ultimately converge? So this is basically that example. It's given by dy dx equal to x plus y, and the slope field looks something like this. Okay. Yeah. So as I was saying, this is the slope field, which is also called a directional field. Is basically nothing, a graphical aid for understanding the differential equation, for understanding the many possibilities of solution of that differential equation. So these curves are showing you all possible solutions of that differential equation, y dy dx equal to x plus y. These curves, these darker curves, are showing you all possible solutions of this equation. All possible solutions of this equation. So what you want to gain from this this visualization, this graphical method to see how your system is evolving, is basically what you want to find is you want to find the slopes of your curve at all points in the plane, so that you can predict how your system will evolve over time. So these are all possible mechanisms by which your system can evolve over time, because all are possibly good solutions for this differential equation. So you don't know which is the exact solution, but you can have an estimate about how your system is going to evolve. Just repeating what I've already said, choosing what you need to do is choose a grid of points, and at each point compute the slope given by the differential equation using x and y values of the point, and at each point draw a short line segment with that slope representing the slope, the angle at which the tangent is present for that curve. So this is what slope fields and different directional fields are. But why do we need directional fields? As I was saying, like we have the equation, we have this differential equation, we know how dx dt is changing over time, but why do we need direction fields? So for example, take this example, dy dx equal to x plus y. So this is a very straightforward equation that is given. So this is a very simple equation, dy dx equal to x plus y. You can easily find analytical solutions to this. There are methods by which you can find analytical solutions to it, and if you do that, you'll find that this is the solution. So y equal to c to the power x minus 1. Your c is the constant here, but this is the form that this equation will take once you integrate this equation. But what happens is, when you're trying to model real life systems, it is impossible to find explicit formulas for solutions of some differential equations, as I had discussed last class as well. When you're trying to do actual modeling of actual systems, you'll find that it is the differential equations that are coming up, they are not very simple enough. They're not like you can do one step of integration and you can find the solutions. What you'll have is you'll have coupled equations of very big equations which you cannot solve by hand. So there we used Euler's method and other numerical methods to find the solutions of such equations. But what it is you cannot, if you have this complex forms of ODEs, it is mostly impossible to find explicit formulas for solutions for those equations. So even if there are formulas, the equations may be so complicated that you cannot use a formula anyway. So In those cases, we resort to this graphical or numerical methods to get an idea about how the solutions of the given equation would behave. Slope fields offer us one such method. So as we saw that direction fields and integral, so these are what are called integral curves. So each of this curve that you see following a particular slope field are what called integral curves, which are denoting the solution of the different solutions of the equation. So a combination of the direction fields and integral curves give us useful insights into the behavior of the solutions of the differential equation if we can't obtain exact solutions. So our whole idea of the using directional fields or slope fields or different type of phase plane analysis is the primary motive of doing the whole thing is basically you do not have an exact solution of the equation. What you want to find is an estimate about how your system would evolve or how your system would behave when time goes on. So you want to have an estimate, you do not have an exact solution. What you do is try to find slope fields or use numerical methods to try to solve the equations. So this is why it is important. So I'll come to phase plane analysis after a little bit when I have discussed after I've discussed the direction fields in detail. I'll go through a few examples. So first let's start with the steady state. Okay. Okay, so let's take the model of fish in tank. So what is the system looking like? So the idea is there are a lot of fishes in a small aquarium or a tank, if you want to call it. So there are a lot of fishes in the tank, and there is a maximum limit to the number of fishes that can be accommodated in that tank. And on top of that, some fishes are basically growing, obviously, like they are reproducing. Some fishes are periodically dying, but instead of dying, we are assuming that some fishes are taken out regularly to have a consistent number of fishes inside the tank. So what our assumptions are? The first assumption is that fishes are growing in the tank with a maximum capacity of K. So K is your maximum capacity, which is also called the carrying capacity. I'm sure you have come across the term carrying capacity used in logistic growth. So basically the idea is wherever there is a system and the system is growing, there is always a state or a maximum capacity of that system to grow to. So the system cannot grow like exponentially for like endless amount of time. It has to have a capacity, and it cannot go beyond that capacity. So there is always a limit to which a system can grow. This is true for every kind of systems. So this example that we are taking, fish in a tank. So that if you think intuitively, like tank is a fixed amount of volume. So the amount of volume that can be accommodated in a tank or an aquarium is fixed. So the number of fishes in the tank, they cannot keep on growing. At one point of time, there will be too much fish in the tank, and there will be not enough resources and water for every fish in the tank. So eventually they'll die out. So there is always a carrying capacity of a system. Same is the concept for our environment. For example, a species cannot grow exponentially and keep on growing till the end of time, because in nature the amount of resources is very limited. So there is always competition for the resources. So there is always a carrying capacity beyond which Mother Nature cannot accommodate or basically keep alive your number of species. So like as is the current state, we as a population are growing so much, there is a scarcity of resources of Mother Nature. So we are seeing different kinds of natural disasters because of that. So we have to always keep in mind that there is always a carrying capacity beyond which the system cannot grow in real life systems. Obviously, while doing modeling, you can assume different kind of stuff. Maybe your system can grow infinitely, but in real life, it is not possible. There is always a carrying capacity. Okay. So, first assumption is this. Second assumption is, as I said, fishes regularly removed from the tank. Okay, and this is done at a fixed rate. Which we can define as basically D. We can assume that to be as D. And the last assumption here is there is no death in the system. So your system is looking like, okay, you have a tank, inside there are fishes, the tank has a maximum capacity of K, and the fishes are regularly removed from, because fishes are breeding inside the tank, the numbers are growing, so regularly some fishes are taken out to keep an equilibrium, and the fishes are taken out with a fixed rate of D, and there is no death in the system. So how will our model look like? So if your X is the number of fishes that is inside the tank, so the rate of change of the number of fishes in the tank, which is denoted by dxdt, it is given as R X in R into X into 1 minus x by k minus d. So where are all these every parameter coming from? So R is your growth rate. Okay, it's simple. We saw that system Rx into 1 minus x last time, so it's similar to that, just extra what we have added here is the k. So if I go to the previous class, I hope you remember this part. So this is the spread of infectious diseases that we modeled using certain assumptions, and this was the equation that we came to, Rx into 1 minus x. If you see here, the equation, I'll write the infectious diseases equation on this side, Rx into 1 minus x. So if you compare the two equations, it's very similar. The extra thing is we have added a carrying capacity, a maximum capacity of k, and we have also added another parameter by which we are removing certain elements from the system as well. So that is given by the d. But in the previous one, if you remember, we assumed that no one is getting cured. So the number of infectious people is not getting decreased by people who are getting cured. But that assumption we are not pursuing here. We are pursuing like we are taking some of the elements out of the system to maintain a number of fishes inside the tank. So this is how your equation is given by, and this is very similar to the infectious diseases equation as well. So just I want to give you an like kind of analogy about how we are doing it. So the only difference is we have added a carrying capacity, and we also have added a rate by which certain elements are removed from the system, which we did not assume in the infectious diseases model. So let's try to solve this equation. So if you have dx dt equal to r into x into 1 minus x by k minus d. This is your equation, right? Now if you want to give, if you are asked what is the concentration, not concentration, here it is number. What is the number of fishes in the tank at steady state? So assume you've been asked this question, okay? You are given this model, this is your model by which fishes are growing inside the tank, and these are the different kind of parameters that has been used in the model. Now you are asked what is the number of fishes in the tank left at steady state. So how do you tackle this problem? So first, steady state. How do we define steady state? If you recall, we define steady state at the point at which dx dt equal to 0. What it means is x is not changing with time. It basically means is x is constant. Okay, so you are asked to find x at which dx dt equal to 0. So it's quite straightforward. So in this equation, you have this equation here. In this equation, what you do is equate this whole thing to 0, because dx dt at steady state will be equal to 0. So this whole thing here will be equal to 0 as well. So how does the equation look like now? So if I scroll down a little bit, so r x into 1 minus x by k minus d equal to 0. Now you need to solve for x from here. This is a quadratic equation. You need to solve it accordingly. So if you just take k common out here and multiply it on the right side, so this will be k r x minus r x square minus d equal to 0. I've just taken k common here, so basically this will be k into rx and minus x into rx, which is rx square, and so this here there will be another k, right? So this is how the equation will look like. Now this is a quadratic equation. Let me write it better in a better way. Rx square minus krx plus kd equal to 0. Now this is the solution, this is the equation that you need to solve. Now this is a quadratic equation. I am hoping you remember, but if not, you can just look up the formula for quadratic equation. So I'll just write it here. So if you're given an equation like ax square plus bx plus c equal to 0, the roots of the equation, basically the points of x at which this holds, the roots of this equation is how we define it, is given by this formula. So x equal to minus b plus minus root over b square minus 4ac by 2a. Now, many of you might be familiar with this equation. If you are not familiar, just look up quadratic solutions, or this is known as what Sridhar Acharya formula, if you want to look it up. So by this formula you can get basically the values of x which satisfied this condition. Basically, if you are given this equation x square plus bx plus c equal to 0, the two values of x which satisfy this equation is given by this formula. So in our case, if you kind of try to compare this equation with the lower one, with this one, so if you compare here, a is given by r, b is given by minus kr, and c is given by kd. Let me know if you are not following. It's just simple. We are just kind of trying to see what are the values of, what are the basically the coefficients of x square. So here the coefficients of x square is r, which is which is denoted by A here. Here the coefficient of X is minus KR, which is denoted by B here, and here the coefficient of C is basically coefficient, not what is the constant here. Here it is C, which is given by KD here. So this is what it is. Now you just substitute these values here. So what you will get is X equal to minus B, so minus of minus KR, so this will be KR, plus minus root over K square R square, so basically B square, if you square this is K square R square, minus 4AC, so minus 4, A is R, C is KD. So this is your numerator, and your denominator will have 2A, which is given by 2R. Now what was our equation? If you remember, I will write it here again. Dx dt equal to Rx 1 minus x by k minus t. This was your equation, and this is your solution of those equations of this equation at steady state, when it is 0 at steady state. Now notice like what you say, an interesting thing. If we take k equal to 1, r equal to 1, and d equal to 1, we take all three equal to 1, what does our solution look like? So if you substitute x equal to k and r both 1, so this is 1 plus minus root over. Now you substitute k, r and d as 1 here as well, so this becomes let's not take d as 1, it will complicate the situation. Let's take d as 0. Okay, k equal to 1, r equal to 1, d equal to 0. So k square r kr becomes 1, k square r square is also 1, and since d is 0, this minus 4 krd becomes 0 as well. So this is 0 by 2 equal to, if you just simplify this, 1 plus minus 1 by 2. So what it means is, one solution is 1 plus 1 by 2, the other solution is 1 minus 1 by 2. So this is basically 1, and the other solution is 0. Now we assumed in this equation, we assumed r equal to 1, k equal to 1, and d equal to 0. Now let's put the values in this equation and see how it looks like. So if you put r, k and d values here, so your dx dt will become, r is 1, so this becomes x into 1 minus x by k equal to 1 again, and d is 0. So what it will become is x into 1 minus x minus 0. So what it becomes is x into 1 minus x. Now do you recognize this model? This is the infectious growth model, right? So what we did was, we used another version of this model to model the number of fish in a tank when you have a removal rate, when you have a carrying capacity. But all these things can be modeled in a much more simpler way, which is basically, if you assume that k equal to 1, the carrying capacity is maximum. What k is giving you, I just want to tell you, k is, which is the carrying capacity. It's basically giving you, if k equal to 1, if it is k equal to 1, what it means is, it can accommodate all elements in the system. It is given actually by a ratio, which is basically, if it is less than 1, if k is less than 1, it's basically, it can accommodate a lesser number of people as compared to the total number. But here, if you assume k equal to 1, it is basically, it is assuming that it can accommodate, your system can accommodate all elements of your system. So that is given by your carrying capacity. So this whole thing that I did, I just wanted to show you key, like all the models, the equations that we use here, sorry, I just ran it over here. The equations that we are using here, so in this case this equation is not very different from the equation that we are using here. So what I want you to know is always think intuitively what the differential equation or what the model is telling you. So the same concept I am applying in infectious diseases model is the same concept that I am applying when I am trying to find number of fishes in a tank. So what is important is, sorry, somebody is trying to enter.
Sorry, sir. Sorry to disturb you, sir.
Yeah.
The recording is on.
Recording is on. After this session is over, I'll upload it on YouTube.
Okay, sir. Sure. Thank you, sir.
Yeah. So yeah. So what I want you to understand intuitively is what the question you are trying to answer. What question are you trying to answer using the model? And if you think the question of how many people will be infected is not very different to the question of how many fish will remain in the tank. If you think intuitively, it's both of them are a closed system. In both the systems, some kind of propagation is going on. So in one case, the infectious model infection is getting propagated, and in this case, in this model, your fishes are multiplying. So if you think intuitively, the questions you are trying to answer are not very different in terms of their mathematical aspects. So this becomes very important to have a clear idea what you are trying to answer. So if you have an idea about what you are trying to answer, you can use existing methods to answer that question, existing models to answer that question even. So that's it. So that's what I was trying to tell you through this example of fish in a tank. Okay, so yeah, let's try another example after this.
Hello.
Yeah.
Here we can say what points are the equilibrium points like that.
So what points are the equilibrium points, you tell me. So for example, so what did we assume here? So this is your model, and what are we assuming here? We want to find x at dx dt equal to 0. So when dx dt equal to 0, what do you call this? This is steady state, right?
Yes.
This is your steady state. So at your steady state, what are the values of x that you got from here? X equal to 1 and 0. 0 and 1. So what you want to do after this is try to have a plot and check at x equal to, this is x equal to 0 is your y axis and x equal to 1 is here. Sorry, x equal to 1 is here and x equal to 0 is your y axis. So what you want to find is, along this region, is your slopes coming inside or your slopes going outside. So if it is, if at say for example at x equal to 1, both your slopes are converging. So your curve is converging from here and another curve is converging from here. So this point will become your stable steady state. But again you have another stable steady state which is x equal to 0, which is your y axis, this one. But you will see that this curve will not touch x equal to 0, it will be asymptotic like this. So what it means is, at x equal to 0, your system will never converge. It will be an asymptotic to the y axis. So it will be very close to x equal to 0, but it will never converge to x equal to 0. So that is what it is meaning. So x equal to 0 will become your unstable steady state and your x equal to 1 will become your stable steady state. But both x equal to 0 and 1, both are your steady states. If you want to define stability, stable or unstable, you have to check around x equal to 0 and x equal to 1 if your system is converging or if it is diverging. Okay?
Okay.
Okay. So let's take these examples only. So let's take an example for a direction field. Say for example you have the same equation. I'm assuming the same equation because it's easier to describe this using this than other equations, but you can do it for any kind of model. Okay, so again for this equation, for this model, we have seen that the steady states are 0 and 1. I am not doing the same thing again, it's same 0 and 1. Now to answer your question, if it is a stable steady state or an unstable steady state, we'll use a technique and we'll see using a table if your steady state is stable or unstable. Say so for example, you check the values of x, you check the value of dx dt, you check the sign of your dx dt if it is positive or negative, and then you give another arrow. Okay, so you know your steady states are at 0 and 1. Now let's take three values. So we'll start off, as I was saying, to check if your steady state is stable or unstable, you need to check around the value of your stable state of your steady state. So here one of your steady state is 0. Okay, so yeah, equal to 0. Now I'll just write the equation here so that it's easier to calculate. Okay, so at x equal to 0, dx dt is 0. There is no sign. 0 doesn't have a sign. Now what it will do is we'll take here a slightly higher value than your steady state. So let's assume this to be 1. Okay, now let's do the calculation here. What is like from 0 we have moved to 0.1. Now what is the value of dx dt at 0.1? Now dx dt, if you put 0.1 here, say you assume r equal to 1 as well. Let's assume for simplicity. So 0.1 into 1 minus 0.1. So 0.1 into 0.9. If you multiply that, it becomes 0.09. So the value of your dx dt is positive 0.09. Okay, and your sign is positive here. So the arrow will be upwards. So it is positive, it is moving away from 0. The slope is positive. Now let's take a slightly lower value. Sorry, this is not a lower value, this is a higher value, by the way. Yeah, now let's take a slightly lower value. Let's take a negative value, minus 0.1. This is slightly lower. Now if you take minus 0.1, you do the same calculation again, dx dt equal to minus 0.1, 1 minus 0.1, minus 0.1. This becomes positive, minus positive into 1.1. Now if you multiply that, it's minus 0.11. One decimal place will shift because there's a minus, there's a 0.1 here. So this becomes minus 0.11. The sign is negative and the arrow is moving away. So what it is meaning is, this is your steady state, your 0 is your steady state, slightly above that steady state, a value which is slightly above that steady state is giving you a positive slope, meaning the system is moving away from the steady state. As with the other point which is slightly lower than the steady state, here also you get a negative slope, which is, it is, so basically this is your steady state in this point, and just above it, it is positive, it is moving away in this direction, and just below it, it is negative, it is moving away in this direction, in opposite direction. So if this is your steady state, your slightly above value is moving away, and the slightly below value is moving away as well. So what can you say for this system? Along this steady state, if I perturb the system slightly, if I increase its value slightly, it will move away. If I decrease its value slightly like this, it will move away again. So what you define is basically a unstable steady state. Right? Now let's do it for the other one. So this we did it for x equal to 0. Now let's do it for x equal to 1. So we'll draw the same table here. X dx dt. Then you check the sign. Then you check which direction your arrow is pointing, which direction your slope is. So here also we'll take 3 values. In the middle will be a steady state. We'll take a value which is slightly above that steady state, say 1.1, and we'll take a value which is slightly below that steady state, which is say 0.9. Now let's write the equation here again. Dx dt equal to x into 1 minus x, right? Now at x equal to 1, obviously dx dt will be 0 because it's a stable steady state and there is no sign. But let's take at x equal to 1.1. So dx dt equal to 1.1, 1 minus 1.1. So 1.1 into minus of 0.1. So if you multiply this is minus 0.11. So the value of dx dt at x equal to 1.1, which is slightly above 1, is minus 0.11, and then sign is negative, so it is coming towards this. Now let's take the other value, which is 0.9. So it's the same, x into 1 minus x, put 0.9 here, 0.9, 1 minus 0.9. So 0.9 into 0.1. So it's 0.09. So at x equal to 9, your dx dt is 0.09. Your sign of the slope is positive, and it is, the slope is positive, so it is coming towards the system. So then what can you say about this stable steady state? So if this is your steady state, and if you are moving slightly above from it, what it is doing is it is pulling it down towards that steady state. It is the same thing. If you pull the steady state down to a slightly lower value, it will pull it up to its original steady state. So this steady state at x equal to 1 is how we define what we say as a stable steady state. Right? So as you can see, for the two steady states 0 and 1, so 0, if you calculate slopes just above and below 0, you'll see that from 0 your system is getting diverged off. But consequently from 1, if you see 1, so slightly above 1, the slopes are coming towards that value 1, and slightly below 1, the slopes are also coming towards that value, which is the same as 1. So basically, if you pull the system in any direction from that steady state, it will come back to that steady state. It will have at least the tendency to come back to that steady state, and that is what we called as a stable steady state. So this we looked at with an example from our basically infectious diseases model. Now let's take another example, which is a slightly different one. So dxdt, let's assume is your model is given by dxdt equal to x square minus 1. So now if you are asked to check what is your what is the basically steady states of this system, and if they are stable or unstable. If you want to find the steady states of this system, you just equate this to 0 because dxdt would be 0. So x square minus 1 equal to 0, x square equal to 1, which will give you two values of x, which is plus 1 and minus 1. Now let's check if either of them is giving you a stable or an unstable steady state. Sorry. Yeah, this session will be uploaded on YouTube, no worry. Okay. Yeah. Okay. So you get two values of x, plus 1 and minus 1, which satisfied this condition x square minus 1 equal to 0. So these are your two steady states. Now let's do the same thing. You check for x, you check dx dt, you check the sign, and then you check the arrow. Let's do it for plus 1. So let's keep the equation here. Go to dx dt. Let's do it for plus 1 at first. So plus 1, dx dt is 0, sign is not applicable. Now slightly increase the value from 1 to say 1.1. Okay. Now your dx dt becomes dx dt equal to 1 point, sorry, so this will become 1.1 whole square minus 1. So if you do 1.1 into 1.1, it comes as 1.21. So this is 1.21 minus 1, which is basically 0.21. So this is a positive slope. So dx dt is 0.21, sign is positive, it's like this, arrow is like this. Now let's take a slightly lower value than 1, 0.9. So dx dt, again calculate 0.9 whole square minus 1. So 0.9 whole square is basically 0.81 minus 1 is equal to minus 0.19, which is negative. So this is basically minus 0.19, which is negative, arrow is opposite. Again, as we discussed last time, so this is your steady state. If you slightly perturb the system, it either moves away in the positive direction or it moves away in the negative direction. So although this is a steady state, this is an unstable steady state. Okay. Now if you do this was for x equal to plus 1. Now let's do it for x equal to minus 1. Same thing, x dx dt, then you check the sign, then you check the arrow. So why I am doing so many examples of this thing is because these kind of questions will come in your exam. So you will not be asked to draw fields like this mostly. So as I was showing you, So this is basically computing the fields at every point. So that much of questions will not come. So they will not ask you to draw the whole field of the graph. What kind of questions will come is basically you have to do this, where you will be given an equation. You want to find the steady state of that equation, and you have to say if it is a stable or an unstable steady state. And this tabular method is very effective in doing that. Okay, so that's why I am going through some more examples for this method with you. And sir has also said ki like this kind of questions will come in the exam as well, so keep yourself prepared from that front as well. Okay, so yeah, so this becomes an unstable. So let's take the other solution, which is -1. So again at -1, dx dt will be 0, sign will be NA. Okay, now let's write the equation again, dx dt equal to x square minus 1. Now we take a slightly higher value than -1. Let's take minus 0.9. That's a slightly higher value than -1, and let's take a slightly lower value than -1, which will be -1.1. Now let's do the same thing. And so first we'll calculate dx dt for x equal to -0.9. Take a whole square -1. What it becomes is 0.81. This minus will vanish because there is a square, and -1, which is -0.19. So dx dt is -0.19. Sign is negative, arrow is coming down. Now let's do it for the other one. It's basically -1.1 whole square -1. It's basically 1.21 -1 is equal to 0.21. So here it is 0.21. This is positive, this is coming inside. So again, this steady state, if you slightly perturb towards a greater value than the steady state, it will tend to come back to this point, to the steady state again. And even if you perturb the steady state to a slightly lesser value of that steady state, it will still want to come back to that state. So this is what is the stable steady state. Now if you do this, say we did this in a small tabular manner, okay, we just checked slightly higher and lower values of the steady state, and we checked how the slopes are. If you do it for the entire grid, so if this is how your function is defined, say you want to define it from here, so say for example this is 1 0, this is 0 1, this is -1 comma 0, this is 0 comma -1. Now you want to check what is the around this region. My pen's not working very well, but please bear with me. Say for example you want to check how your system is behaving between these 4 points. So what you will do is you'll chop it up into small points like this, and you will calculate direction fields, basically the slopes, if it is positive or negative, and put it accordingly here. Say for example it is here, another slope will be something like this. So at every point you can calculate slopes like this, and you can put in arrows. So that is what will get you a direction field like this. This is what you get when you do it for all the points. This we are just doing for the steady state points and slightly higher and lower values. So total 3 points we are doing. If you do it for the entire plane, this is how you will get the result, and this is how basically your different solutions will look like. Okay, so I hope this steady state stability and unstability is clear. If so, we can move on to another example, which is basically the one for the phase plane analysis. Okay, and null lines. Okay, let's do that. Okay, so let's assume a predator-prey system. Okay, so predator prey system. Okay, now let's assume X is the number of, sorry, I'll write it in short. X is the number of prey, Y is the number of predators, K1 is the growth rate of prey, K2 is the rate of consumption of prey by predator, and your another constant K3, which is the rate constant for the death of the predator. So what are the things that you are looking at? So you want to model this thing with the help of the number of prey, number of predators. Also you have kept three different rates, three different things that you are considering. One is the growth of the prey, one is the rate of the consumption of the prey by the predator, and also the rate of the death of the predator. We are not considering that the prey is also dying for other causes other than being eaten by the predator. We are assuming that it is only dying in the hands of the predator here, but there is a rate constant associated with the death of the predator as well. So in one side we are taking care of that. So your system will look like, so if your X is the number of prey and Y is the number of predators, so basically the rate of change of number of prey will depend on the growth rate of prey into the concentration of prey minus the rate at which the prey is being eaten by the predator, which is dependent on both the concentration of the predator and the prey. This is for the prey. Now for the predator will be dy dt equal to, it's the same concept, it is increasing with the rate of k2 into xy because it's the rate at which the prey is getting eaten by the predator, and also it also has its own death rate. So this will be minus k3 into y. So this is for predator. Okay. Now let's
Hello.
Yeah.
Can you explain again the model of prey?
Okay.
How you found the equations?
Okay. So you have assumed that, sorry. So for the prey equation, so you want to see how the rate of change of prey is happening. So dx dt is giving you the rate of change of the number of prey. Okay. So the number of prey, what it depends on? It depends on the initial number of prey, which is given by x. So this is that initial number of prey. Also, this is basically the initial number. After that initial number, the prey is getting eaten up. So that's why this negative sign. So obviously the growth rate of the prey. So what dx dt is giving you is the growth rate of the prey. How prey is evolving, how prey is growing. So the growth rate of the prey will depend on the initial number of preys, which is given by k1x, and it also will depend on the number of prey that is getting eaten up by the predator, which is given by this basically expression k2xy. Now K2 is the rate of consumption of prey by predator, and that depends both on x and y. So that's why you have a K2 into xy. And why negative? Negative because this part is basically how much your prey is getting eaten by the predator. So basically this part of your equation is telling you how much prey is getting diminished due to getting eaten by the predator. So that's why that negative sign. Okay, so the concentration, the number of predators, number of preys that is present, that is dependent on both its initial number of preys that were present, and also if you have to subtract the number of preys that were eaten up by the predator. So that is how this whole equation comes. Okay.
Okay.
Okay. So if we move on, let's assume for simplicity for both the equations, let's assume K1 and K2 both equal to 1. But I use K1 and K2 to give an idea because in real life K1 and K2 will not be equal to 1. There will be some parameters associated with, there's some values associated with these parameters. But for our simplicity, for our like trying to get the equation solved easily, we'll use K1, K2 both equal to 1. So both our equations become x minus xy, and dy dt becomes xy minus y. Now if you are asked what
K3 also 1.
K3 also 1, yeah. Basically all the parameters that we assumed, just to have it simply like this, we are assuming those to be 1. Okay, so there is no other reason. There can be other values associated with it. If you have 1, it is easier to solve. Okay. Yeah. So if you are asked what is the number of prey at steady state, now if you are asked a question like this, what is the number of prey at steady state? Now you have two equations like this. One you have for the rate of change of prey, one you have the rate of change of predator. Now if you are asked a question like this, what is the number of prey at steady state, the next question that you should ask is basically whose steady state? Is it the steady state of the prey or is the steady state of the predator? So there are two different steady states here. One is for x and the other is for y. So I'll write it here. So when dx dt you are assuming to be 0, which is basically steady state of x only, that is what is called as the null cline of x. Okay. Similarly, when you are just assuming, just looking at the steady state at y, where dy dt equal to 0, that is the steady state of y, and which is basically the null cline of y. Now these are individual steady states. So when you are equating dx dt equal to 0, that is only dx dt equal to 0. dy dt can be anything else. Okay, it can be a positive, negative, or even 0 itself. So when you are looking at the steady state of x, you are only considering, or you are only interested in if x is changing with time or not. If it is not changing, if x is not changing with time, then that point is your steady state for your x. But what about y? Right? So when you are looking at y, it's in the similar way. You are just looking at y, where y is not changing. You are not interested in x. So when you are looking, but your system, the major thing to remember, your system is dependent both on x and y, right? Your system does not only depend on x, or it doesn't only depend on y. It depends on both. So this is basically the steady state of x, and steady state of y is given like this. Now you can imagine how the steady state of the system will be given as. So steady state of the whole system, which includes both x and y. It's very intuitive. It's basically the points at which both x and y have steady states, right? So now recall, when x has the steady state, it's called the nullcline of x. When y has the steady state, it's called the nullcline of y. So at which point will the steady state of the whole system be? It will be at the points at which the nullcline of x and y meet. So what does this mean? So say for example, let's try to solve this. Okay, so dx dt, I'm writing this equation again, x minus xy, and dy dt is xy minus y, right? Now first, when you're trying to find the steady state of the whole system, you need to first find the nullcline of x, then the nullcline of y, and then ultimately you'll find the total steady state of the system. So first find the nullcline of x. Okay, how will you find dx dt equal to 0? Just equate it to 0. So x minus xy equal to 0. Now you solve this. X you take common, 1 minus y equal to 0. So your solution is x equal to 0 or y equal to 1. Okay, this is your solution for the nullcline of x. Now let's take a look at the nullcline of y. dy dt, sorry, given as xy minus y, we equate it to 0, we take y common, x minus 1 equal to 0, x equal to 1, y equal to 0. So now let's try to plot this. So this is your nullcline of y, and this is your nullcline of x. Okay, now let's try to plot this in the graph. Let's take this as the graph. Sorry. So this is your x-axis, this is your y-axis. Okay. Now let's first plot the nullcline of x. X equal to 0 and y equal to 1. So x equal to 0 is basically your y-axis. So I am marking the nullclines of x using blue. Okay, just to remember. So this is one nullcline of x, which is basically x equal to 0, which is the y-axis. This is one nullcline of x. The other nullcline of x is y equal to 1. Y equal to 1 is basically parallel to x-axis. So if you assume this to be 1, 0, this is the other line. So this is y equal to 1, and this blue line is x equal to 0, right? So you have plotted the two nullclines of x. Now let's try to plot the two nullclines of y. Okay, now I'll plot it in red. So nullclines of y are x equal to 1 and y equal to 0. So y equal to 0 again is this, the x-axis again. Okay, so this is your y equal to 0. I'm writing here y equal to 0, and x equal to 1 is parallel to the y-axis. So, oh sorry, I have written wrong here. This is basically 0, 1, not 1, 0. 0 comma 1. Okay. Yeah. Now this is y equal to 0. Now x equal to 1. It's, if you assume this is 1 comma 0, it's a line passing through here. Sorry, I'll erase it. This is 1 comma 0 and this is your line. So the red lines indicate null line of y and the blue lines indicate null line of x. Now how is the steady state defined? I'll just write it here in below. Steady state of this whole system is at those points at which null lines of x and y meet, right? So the blue is the null line of x and the red is the null line of y. So where is the stability of where is the steady state of your system? It is right here at the point where the null line of x and y meet, which is basically the point 1 comma 1. Okay, so just to give you just to recap. So first we talked about how you can see steady states for independent systems like dx dt, and there is that the whole function is of x. That we saw how we can see steady states if those are stable, unstable. Here your system is dependent on both. There are two dependent variables here, dx dt and dy dt, with basically x and y are your dependent variables here. Now if you have a system which has something like this, which is basically multiple dependent variables instead of one, how you can find the steady states? You find the null line of one variable and you find the null line of the other variable. Where these two null lines meet, it's basically where both of them are 0, both dx dt and dy dt are 0. That is the point of your stability of the system. That is the steady state of the system. That is where the steady state is. Okay, so I'll just write it down here or in another page maybe. Just a second. Okay. So how do you find if there are multiple dependent variables follow identify where dx dt equal to 0, which is basically the null line of x. Just remember these terms: null lines, phases, direction fields, slope fields, because like you may understand what these are, because but like in exams the questions will come using these words, so it's better to get accustomed with these words from now on. Okay, so this is nothing but dx dt equal to 0. We have a glorified name for it, which is the null line. Okay, null line of x. Similarly, identify where dy dt equal to 0, which is the null line of y. Next, mark, sorry, the null points. Okay. Now this is how you identify basically steady states in a 2D system where the system is dependent on both x and y. Now you found the steady states. How do you know those are stable or unstable? It's the same way. It's the same way how we did it for single systems. We checked points around those steady states if the system will go away from it or the system will come back towards it. It's the same way we compute those slopes in and around dx dt equal to 0 and also in and around dy dt equal to 0, and we check those points whether the system in those points is coming back to the steady state or it is moving away from the steady state. The concept is same. Okay, so if you want to identify those, your fourth step would be away from the equilibrium points, which is the steady state equilibrium points, which is basically the steady states. Determine the trajectory of the system, right? Whether moving towards or moving away from the system, from the steady state. How do you do that? You compute slopes around the steady state and then check the signs of the slope. Is it positive? Is it negative? Right? Just as we did for a single dependent variable x versus t, similarly we can do for both x and y versus t. Okay, so the whole idea is the steady state, your system should not change from time to time. Your dx dt or dy dt, whatever your dependent variable is, it should not change with time. And on top of that, if it is a stable steady state, if you perturb the system slightly, it will come back to that steady state. If you perturb the system and it does not come back to the steady state, it moves further away, it's basically the unstable steady state. Okay, and what are null clients? Null clients are basically in systems where there are multiple dependent variables, null clients of the points at which individual variables have zero differentials. For example, dx dt equal to 0, basically that variable is not changing at that point. So at those points are called the null clients of x. Similarly, for dy dt equal to 0, those points will be called as a null client of y. And where these null clients will meet, basically where both dy dt and dx dt will both be 0, those are the stable points, those are the steady states points. Okay, stability on if it is stable or not, you will identify by checking the points in and around the slope and checking the signs of the slope in and around the steady state. If it is if it is converging, then it's a stable steady state. If it is moving away from the from that steady state, it's an unstable steady state. Okay, so
Hello?
yeah,
I have a doubt.
Yeah, sure.
What if the null claims are does not meet anywhere?
Okay, so this is a very common thing that you'll notice. The null clients will maybe not meet anywhere. So what that means is the system is not in a steady state where either of the variables is in a steady state. Okay, so the system is never in a steady state. So either your x is changing or your y is changing. So just I'll write it here. It'll make you better understand. So what does dx dt equal to 0 mean? Dx dt equal to 0 meaning x is not changing with time, with respect to time. Okay, same dy dt equal to 0 means y is not changing with time. Okay, now let's assume this is a line for dx dt equal to, I'll draw a curve like so. So for example, let's assume this is a line for which dx dt equal to 0, and this is another line where dy dt equal to 0. So along this line dy dt equal to 0, and along the green line dx dt equal to 0. So here these are both your null clients, and your null clients are not meeting. So what it means at every point dx dt equal to 0, dy dt is not equal to 0, right? Because if both were 0, they'll meet at some point. If it is not meeting, it means is along every point at which dx dt equal to 0, dy dt is not equal to 0. So what it meaning is, when your x is in a stable state, your y cannot be in a stable state, or the vice versa. If your y is in a stable state, your x cannot be in a stable state. So basically your system will not be in a stable state, in a steady state ever, because both your x and y will never be constant. Either your x will be changing or your y will be changing. So your system does not have a steady state. Understood?
Yes.
Okay, right. Cool.
So we can say the model always should be in a steady state or like that.
Yeah, your model
That's a possibility also there.
your model will be in a steady state where both these two conditions satisfy. Okay, both, not either or. Right? If it is either or, then it is just null cline. It is just a null cline of x or just a null cline of y. But both have to be 0 to tell that your system is in a steady state. Okay, both have to be 0. It's not either or.
Okay.
Okay, cool. Okay, done with this. Direction fields we talked about, and an extension of the direction field was phase plane analysis, the one that we did with both functions. So as I was saying, you have two dependent variables here, x1, x2. There I was saying x and y, but basically the phase plane is a glorified direction field technique, which is just with, instead of one dependent variable, you will have two dependent variable. So you want to find steady states of independently of individual variables, and also you want to find the steady state of the whole system where both these individual dependent variables will have a steady state. Both dx dt and dy dt will be 0. So that is what is called as the, basically if you plot x and y out in a 2D plane, that is what is called a phase plane. And basically the curve basically with which, say for example, if this is a phase plane plotting x and y, the curves that basically show you this evolving of the system with time are basically called the phase plane trajectory, the trajectory of your system. Okay, And basically the phase plane is a glorified version of the direction fields or the slope fields. In direction field or slope field, you are doing it just for one variable, one dependent variable. In the phase plane analysis, you are doing it for both, but the concept is same. Your system will be in a steady state where it only and only if all of your components in the system are in a steady state. If either of your components are not in a steady state, the whole system cannot be in a steady state. The whole system will only be in a steady state where both x and y are in steady states. If only x is in a steady state, it is called the nullcline of x. If only y is in a steady state, it is called the nullcline of y. And where both these nullclines meet will be the steady state of that system. Once you get the steady state of the system, you want to find out if the steady state is stable or not. What you do is simply you check the points around that steady state if the system is diverging from your steady state or it is converging back to your steady state. If it is converging back, it's stable. If it is diverging, it's unstable. Okay, the concepts are same across the different methods that we are using, but the methods are slightly different depending upon the number of variables and your model, but the concept is same. The concept will be same all across. Okay, so that's all for the discussions that we had, but we'll also solve 4-5 questions that sir has asked me to as well. So let's start with the first one. Find the stable steady state of the following ODE: dx dt x squared equal to x squared minus 9. I'll give you a minute, then I'll solve it. Okay. Hope you have written down the question. I will solve it here. Okay. Dx dt is given by x square minus 9, right? Now at steady state, this is equal to 0. So x square minus 9 equal to 0. So there are two values of x satisfying this solution, plus minus 3. So your steady state is at both at plus 3 and minus 3. Now you want to check which is the stable among these two. Do the tabular method, that is the most simplest one that you can follow. You have x, you have dx dt, you have sine, and you have the arrow. Okay. Bigger. Now this is your steady state, x equal to 3. So let me write the equation here, dx dt equal to x square minus 9. So dx dt is 0 at your steady state, so there is no sign. So there is no sign. Now you take a slightly higher value. So let's take 3.1 here. Now I have to check what's the square of 3.1. 3.1 into 3.1, it's basically 9.61. So if you put 3.1 here, so dx dt equal to 3.1 whole square minus 9. So basically 9.61 minus 9, it's basically 0.61, which is a positive slope. 0.61, it's positive, arrow moving upwards. Now let's take a slightly lower one, 2.9. Okay, same dx dt equal to 2.9 whole square minus 9. So 2.9 into 2.9 is basically 8.41. 8.41 minus 9, it's minus 0.59. So on a slightly lower value, the slope is negative, so it is a minus here, and the arrow is going down. So this steady state is unstable because slightly above it is moving away, slightly below it is moving away as well. So this is, although a steady state, it's an unstable steady state. Now let's check for minus 3. Do the same thing. This is your x, this is your dx dt, sorry, no. This is your sine, sorry, this is your arrow, right? So x is minus 3, let me write the equation on this side here, dx dt equal to x square minus 9. So at minus 3 it's 0, sine there is no sign. Now let's make it a slightly higher value, say minus 2.9. Again dx dt equal to minus 0.9 whole square minus 9. We have already calculated here, I am not calculating again, it's minus 0.59. Minus 0.59. So 0.59. The sign is negative, arrow going down. Now let's take a slightly higher value, a slightly lower value than minus 3. Minus 3.1 is a lower value than minus 3. So here also dx dt will be minus 3.1 whole square minus 9. This we have already done before because minus 3.1 whole square is same as 3.1 whole square. So this comes up to be 0.61. This is 0.61, this is positive, and this is coming inside. So what is this? This is the stable steady state. So your answer is minus 3 is the stable steady state. Okay. This was a very this was quite a straightforward problem, but problems like this will come in your assignments as well as your exams. So try practicing this kind of problems. Okay. So this was the first one. Okay. Now let's try this second one. Okay. Write down the equation, then I will try to solve it. I hope you have written down the equation. Now let's try to solve it. This question number 2. Okay. So dx dt is given by alpha into 1 by 1 plus y minus x, and dy dt is given by beta into 1 by 1 plus x minus y. Okay. Now you are asked to find the steady states of these. First you have to find the null lines of each. So let's try with the first one, dx dt equal to 0. Which implies alpha by 1 plus y minus x equal to 0. Alpha minus x minus xy equal to 0 implies x into 1 plus y equal to alpha. Same, let's do it with dy dt. dy dt equal to beta into 1 by 1 plus x minus y. Now this is equal to 0. So beta minus y minus xy equal to 0. Okay. Now we take y common from here. Y into 1 plus x equal to beta. Now this is for y. Let me write down the x1 here only. So x is basically, the other one is x into 1 plus y equal to alpha. Now alpha or beta are given as parameters. For our simplicity, let's consider them as 1 because these are constant only. So we can consider them as 1, and in the question also it is given ki they are both greater than 0. So let's consider them as 1. Okay. Now what it becomes, these two equations are basically, the first one becomes xy plus y equal to 1. The other becomes x plus xy equal to 1. So this is the null line of y, this is the null line of x. So how will you find the steady state? It's simple, where these two null lines meet. Now this is an equation that you need to plot in xy coordinates, this is another equation that you need to plot in xy coordinates, and then you need to check where these 2 points are meeting. So since this is not a very straightforward plot, so I have already used a plotter to plot it. So if you can see, so in the question also it is assumed that xy is greater than 1, so we'll consider the upper plot, not the lower plot. So both are hyperbola, but we'll consider the upper plot. So the red line is basically y plus xy equal to 1, and the blue line is x plus xy equal to 1. So these 2 points meet here. See here, the approximate value is 0.62, 0.62. So your steady state is basically at this point of the system is at steady state at this point 0.62, 0.62, where both of your null lines meet. Okay. So this is an example of how you can find the stability of the system if by calculating individual null lines and seeing what they are meeting. Okay. So this is how it is done, and this is a plotter, so you can use it. I'm just giving it here.
Actually, there is another point also there, right?
Another, sorry?
Another intersection point is there, right?
Yeah. So this, the whole curve looks like this. So here is one point, this is the negative point of that, and here is the another point. But in the question, since it is given ki x, y are both greater than 0, so in this case this part is both x, y are less than 0. So we are not going to consider this. We are only considering the upper part, the one in the first quadrant. So this one. Okay.
Okay.
You can use tools like this to plot. It will help you plot these problems, these equations, and you can easily visualize this. So just you have to add it, and you just write it like the xy equal to say 5. It will add another plot. Okay. So it's quite easy. Okay. This was the second one. Let's move on to the third one. Okay, I hope you've written down the question. Now we'll try to solve this. Okay. Okay, the third question. You're given this equation dx dt equal to a into x by k plus x minus x. This is your given equation and you're asked to find the all possible steady states of this model. So regularly you equate this to 0, then you try to solve for x. So what you do is you take x common, you right. So from this equation there are two values of x. One is x equal to 0, the other one is basically a by k plus x minus 1 equal to 0, a by, which implies a by k plus x equal to 1, implies k plus x equal to a, and ultimately x equal to a minus k. So there are two steady states of this system. At x equal to 0 and at x equal to a minus k. Okay. These are pretty straightforward problems. You will be given an algebraic equation with dx dt. You need to equate dx dt to 0 and solve for the algebraic equation to get the values of k. Quite straightforward. Okay. Okay. Let's move on. Yes. Can you answer this question? And I want to hear your logic.
Ultimately, they will finish at 0, 0 or something.
Yeah. So that is the idea. So the question is to find the value of x and y when t tends to infinity. So t tends to infinity means at the end of time where your system will converge. Your system will converge at the steady state, which is already given at 0 and 0 and 0. Doesn't matter at t equal to 0 where they start. They can, here they are starting at 3, 3. It can even start at like 5, 5. But ultimately, if the steady state is at 0, 0, at t equal to infinity, you can expect that system to come to 0, 0. Okay, that's the whole concept of steady state, because here also, if you notice, the steady state here is a very stable one, because if you move away from it, it will pull you back here. If you move away from it here, it will pull you back here. So it's a steady state, and it is attractive in nature. So wherever you start, that doesn't matter. If the only stable steady state is at 0, 0, at t equal to infinity, the system will come and converge at 0, 0. That's the idea. Okay.
So here the value of x and y are given to confuse us.
Yeah. It doesn't matter if it starts from 3, 3, it can start from 4, 4 as well. It won't matter. At t equal to infinity, it will come and converge at 0.
Okay.
Okay. Yeah. Okay. So we are done in terms of the things that we needed to discuss. But before going, I'll discuss a little bit about JSIM. So this is the GitHub page that Sir shared with me. So I don't know. Do you guys have seen this page before? If not, please look into this GitHub page. So this page has all the codes, JSIM codes that has been used for this course. We'll see more JSON codes later down the line, for the other weeks that we go on. But you can always try to use these codes and try JSON on your own. So I'll just try to give you how this works. So say for example we take the fish model. This is the fish model. I'll just copy the code from here. So this is the first JSON page that opens if you open JSON. This is on Mac. If you are on Windows, you download the Windows version and try to open it. If you face any issues with JSON, write to me or sir, we can help you out with that. So I'll just give you an overview of how this works. So here I've already loaded 2 models. I'll add another one. So let's add another new model here. It's model 3. So if I go to model 3 here, this is the source, this is the page where I can paste the code. Okay. So I'll come to the explaining of the code later, but as you can see, this is the equation. So x is to t is what is it is denoting is dx dt is r into x into 1 minus x by k minus t. The equation that we just tried to solve using normal methods. But in this one we'll simulate it using JSON. So this is the model. You can find other models in the GitHub repository as well. You can tweak it on your own and you can try simulating it. So once you have the code, you compile it. So after compilation, these are your basically the parameters that comes here. And if you want to see the data, so choose the data from here. In this case our model 3 is the data here, and then you want to check say for x versus t, and then you run again, then you go to the source and try to compile again. So this is how the plot comes out. So as you can imagine, can you tell me what is this point at which this stagnates? This is the equation. This is the equation.
Carrying capacity of
exactly. It's the carrying capacity is the value of k. So if you just if you just change the value of k, so as you can see this is at 100. If you change the value of k say for to 70 and run again, sorry, I think some other things changed as well. Let's go to the model page. Run this. Okay. I think if we are putting k equal to 70, it is coming at negative. That's why these values are coming. So I'll do it on another page. Just a second. Add new model. Change the model to model 4. Yeah. So this k is the carrying capacity, and that is the where it the point at it stagnates. You can take out the data from here as well. Text, you can see the t versus x, all the values are given. So it is incrementing by 0.01. If you recall Euler's method, we incremented by 0.01 to check the values of x. So it is doing the same thing. It is incrementing the value of t by small amounts and trying to check what is the value of x. That is how it is getting the graph. Now if you want to add another thing, you want to check, say for example, how 1 minus x is looking. Just add it, it will come it like this. So, or if you want to check, say, how x plus 5 is looking, it will come it like this. Okay, so you can tweak these things and you can check with different parameters. You can tweak the parameters here as well. You can check the parameters and tweak it and check how the different curves are coming like from different type of models. So GSM is a very useful simulator which will readily give you the simulated results along with curves and how basically your system is behaving. And this is the code for JSIM. I'll just go over this code quickly. What are the components of this code? So first is something that you define. Just a second. Yeah. So the first is something that you define in the model. So this is the name of your model, fish model, and math is denoting the type of the model. So I'll just quickly write this down so that it can be useful in later. Okay. So this is about JSIM. First is you have to define your model type. Okay, this is for our cases it's math. Next is this real domain T. This is basically your independent variable. This is the first thing that you define, and in real domain what you are telling is basically T is real, it's not complex or anything else. So that is how you are defining your independent variable. So first you define your model type, then you define your independent variable, which is given in the real domain. Sorry. Okay. Third thing, what you define is basically your dependent variable. This is your dependent variable. So here also real means it's in the real space. There are no complex things involved. Complex as in I and everything. Those are not involved. All real spaces. So next, what you define is the dependent variable. So that, just remember the syntax of the dependent variable, how you define. It's basically given as x of t. So the moment you put in like this, the program assumes that x is a function of t, so it's dependent on t. So this is how you define dependent variables. Okay, so these are some syntaxes that you need to keep in mind, because in exam what will happen is you will be given a code with certain wrong syntaxes, and you will be asked where in the code there is wrong, and where will you get the error. So these kind of questions will come. So say for example you are defining a dependent variable just by x, it will not assume that this variable is dependent on t. You have to give t in brackets. So these kind of syntaxes you need to slightly remember, because you will not be asked to write full codes of JSIM. What will be given is small snippets of codes of JSIM, and you will be asked to say what does this code do, or what is the mistake in this code, stuff like that. So first to define the model type, name of the model, your independent variable, then you define your dependent variable like this. And the most important thing is, after everything there is a semicolon. Just look at it. After everything there is a semicolon. It defines as a delimiter. So you have to put semicolon at the end of every line. So anything you define, after that you have to put a semicolon. So you define your model, then your independent variable, then your dependent variable, then you define your parameters, R, A, K, whatever is your parameter, you define them in real values. Check the syntax here as well. It is given like this: real R equal to 1, real K equal to something, real D equal to something. And after that, after defining the parameters, define the initial value. How do you define the initial values? The syntax is like this: when, then this is first bracket, t equal to say t dot min. You have defined t min before. Then you close this bracket. Then you open a curly bracket like this. Then you say what is the value of x there, and don't forget this semicolon. Okay, this is basically the initial values. This is how you define the initial values. So keep these small syntaxes in mind. This might come in the exam. And at last you define the OD, and just to remember here, your dx dt is written in this form, x colon t, and your equation, wherever you have a multiplication, you have to give a star, and at the end of the equation you give a delimiter, which is the semicolon. Okay, so you can try practicing different types of models using these codes. You can check out the codes and everything. You can use plotters like this Desmos plotter and other plotters. There are other plotters as well. So for example, this is another plotter where you can put in the equation here. It will show you the phase plane as well. So I'll put this in the chat box as well if you want to use. So these plotters you can use while you are studying or while you are practicing for different things. But the thing is, these plotters, this websites will not be available to you during the exam. So it's better to have an understanding how the equation is looking like. If you can just have a generic curve, if you can understand how the curve will look like. So plotters and all can help you while you are studying and everything, but in the exam those will not be allowed. You have to do it on your own. And the questions there will not require you to those will not be as difficult that you will not be able to plot or something. You will be able to plot if you have the basic knowledge. Okay, that's all from my side. If you have any questions, you can ask.
Yes.
Yeah.
Actually, I have some doubts.
Yeah.
You have shared some things like JSON code like that, na?
Yeah.
So in the lectures also we are seeing phase diagrams.
Okay.
So from is there any software to create that phase diagrams?
Phase diagrams is actually I have a it's not a software. It's basically I'll show you the thing. So basically this is the plotter. You can use this. You open this, you go to dxdt and you say x plus xy, dy dt is y plus xy. And then you can try it. So basically, can you open the link?
Yes, I have opened.
So there you can see you have to give the dx dt how it is looking, dy dt how it is looking, and then you click on graph phase plane. It will show you the phase plane. So the one that I showed you from earlier, the one that I asked you the question ki, where it is going to the system is going on t equal to infinity. So that kind of phase plane it will generate when you put in the equations there.
Okay. And also I have some doubts regarding models.
Yeah.
Actually, in the first week of lectures, Sir said when we are going to model the system should be homogeneous.
Yeah.
Okay. But I have seen some papers which are dealing SAR models like that. In that models, in the susceptible equations, they have considered the total population like n as a total population. But that system, I mean that equation is inhomogeneous, right? When we are considering.
So yeah, complete your question.
So what is the need to consider only homogeneous?
Okay. So any kind of assumptions that we make on models, be it homogeneous or we made other assumptions as well, ki there is no death happening in the community while the infection is going on, and the other assumptions that we make, every assumption, the idea behind that assumption is it makes our model a little bit simpler. We can always assume that there is a heterogeneity in the population. Obviously, that is the real case. When you are trying to do real models, you will not assume that the system is homogeneous because it's not the case. So in those cases, what happens is we have to include extra terms in our model, in the dxdt or the dydt or whatever model you are trying to do. You have to include extra terms with their rate constants. So what happens is your equation keeps getting bigger and bigger. So the lesser assumptions you have, the more complex is your model. So when sir said that we are assuming the system to be homogeneous, what he is trying to say is we are assuming the system to be homogeneous so that we can make our model a little bit simpler. That's all we are trying to do. We are trying to make our model simpler so that we can solve the model easily and we can have answers. You can do with no assumptions as well. You can try to incorporate as many caveats as you can think of, but what will happen is your model will keep getting bigger and more complex. So since this is an introductory course, that's why sir took all the assumptions in which we can have a more simpler model and we can solve it easily. So that's why he took. But as you're right, if you read papers, there are SIR models, there will be, if you read, there are SIRV models. So where they take vaccination into account as well. The vaccination brings down the infection. So there are different kinds of model with different kinds of assumptions. It's just what question are you trying to answer and how complex do you want your model to be. That's the whole idea. So if you want to model to be a simple model but not exactly mimicking the real life situation, but just to get an idea, you can make assumptions like this, that the system is homogeneous, there are no deaths in the system, the other kind of assumptions as well. It's just about how complex you want to make your model. That's all.
Next question is,
Yeah.
if the model we are considering some parameter values, right? So as mathematicians, what we have normally done is we assume some values. The parameter values are we assume.
Yeah.
Okay. But many of the researchers expecting real data. From the real data, how we can make that parameter values, because in real data means we have lots of raw data, right? Like that.
Yeah.
So we particularly take one point. For example, if we are taking growth rate is equal to 1 means we are only taking that value.
Yeah.
But maybe we have lots of values for that, right?
Yeah. So the parameters, the thing is, in your model, the parameters will define how your systems will evolve. So the parameter is very important. Now, the value of the parameter should be a realistic one. So for example, your carrying capacity should not be greater than 1, right? So, or there can be other parameters. Say for example, you are looking at a chemical equation or chemical reaction in which the enzyme concentration is very low, so low that your the system, the reaction cannot take place. So there are some realistic parameters. The parameter values that you are assuming has to be realistic in nature. So that's why what they do is they take real data and they want to simulate, they want to get that real data using a simulated model. So what they do is kind of try to back calculate, if using my model I want to get a real life data, exactly mimicking a real life data, what are the parameters that I should use in that model. So it's kind of doing a back calculation and trying to figure out what kind of parameters should be ideal for a system like that. Also there will be other literature resources, previous researches and everything people have done. People have already studied these kind of systems and they've decided on parameter values. They know what kind of parameters will have what kind of values. So those you can use while trying to do your model. But if you are trying to find parameters from your existing data, what you'll do is you'll try to fit your model to the existing data and then you'll back calculate the parameters, what we call as parameter estimation, right? In statistics there is something called parameter estimation. There are many ways to do it, but what it's basically back calculation. You have a real world data and you have an hypothesized model, so you fit the model to the real world data and you try to back calculate what should be the parameter values so that my hypothesized model can fit my real world data. That is how the people do it in
how
research.
it can be done. Actually, that's the question. That's my question.
That's a bigger topic to discuss. It's you are from a mathematical background, so you should know something about parameter estimation and other stuff, maximum likelihood estimation, other Bayesian processes. So basically what they do is, so you have your model data, simulated data, and you have your real data. What the majority of the techniques do is they try to find the mean squared error between these two kind of data, and using that mean squared error they try to minimize that mean squared error by tweaking the parameters. So at which parameter the mean squared error between your real data and your observed data is the minimum, that will be your ideal parameter. So there are many methods to do this. One of them is MLE. There are other statistical. There is a whole branch of science for estimating parameters. So I cannot explain all of you to you now. But the idea is you kind of measure the error between your model simulated data and the original real life data, and you try to bring down this error as much as possible by tweaking the parameters. Okay, so there are many methods to do it, but this is the whole idea.
Okay, and the last question is, he said the malaria, that type of models are controlled by some vector functions. Like there, he said mosquito is a vector sum. I forgot the term. He mentioned something vector for that mosquito.
So in terms of infections, vector of an infection is basically the creature that is carrying the infection. Say for example, dengue is an infection that is propagated by mosquitoes, but the dengue virus is not made by the mosquito itself. So what the mosquito does, it carries the dengue virus to other people and gets them infected. So it is the vector of that disease. So the creatures that carry the main ingredients of a disease, be it the virus, be it the bacteria, be it whatever is causing the disease, if some other creature is carrying that and propagating that disease, so that we call as a vector. So it's a biological term, you can look it up.
So can we call, if we are modeling in flu model, can we say humans are vectors?
Yeah, we can say. We can say for COVID-19, humans were vectors. So we were the ones, we were, okay. So, one thing. So in terms of dengue, malaria kind of diseases, you have to notice that the mosquito doesn't itself get infected with that disease. So the kind of disease we have by the malaria pathogen or the dengue pathogen is very different from the kind of reactions the mosquito himself or itself has. So that is something that you have to keep in mind, that vectors are the creatures that are carrying the disease, but not all vectors are affected equally. So the mosquito doesn't get affected by the dengue virus itself. It doesn't hamper its lifestyle, it just propagates it to other people. So that is the role of a vector. The ideal vector would be that one which will not get affected itself, but it will propagate to other people. But you can also call in that context, we can call ourselves as vectors for COVID-19, but the exact definition of vector doesn't sit to us, because COVID-19 affects us as well. Okay, if it were some kind of a virus that doesn't affect humans, but humans are carrying it, and they get the cats or dogs are getting infected by that virus, then we can call us as proper vectors of that disease. We are carrying the disease, we are not getting affected ourselves, we are affecting other people, other species, to be very precise. Okay.
Okay. Thank you so much for answering my questions.
Okay. Thank you for sitting through 2.5 hours. Okay.
One more thing.
Yeah.
Can you share your mail ID and YouTube channel again?
Yeah, sure. I'll share my. This is my mail ID and YouTube channel. I'll just pull it up and share. Okay.
Thank you.
Okay. Thank you for joining. See you next Saturday. Okay. Thank you.
Thank you. Bye.
Bye.